What would happen if you squeezed the Earth down to the size of a tennis ball? No one is claiming that this will happen anytime soon, but the thought experiment raises a fascinating prospect. The Earth would be significantly denser than any natural substance if you could squish it down to this size. You'd think it'd be well on its way to turning into a black hole by now. However, there's a chance you'll get something utterly unexpected: a Preon star. According to most physicists, quarks are the fundamental building components of all matter. However, some scientists believe quarks may contain particles known as preons that are well beyond the detection limits of current and most future particle colliders. Preons are hypothetical particles that have been postulated to be the building blocks of quarks, which are, in turn, the building blocks of protons and neutrons. A Preon star, which isn't actually a star, would be a clump of matter made up of quarks constituents and held together by gravity. A group of researchers described two ways for detecting preons in space, in the form of preon nuggets that could also be a kind of dark matter. Even though many scientists are skeptical of the existence of preons, the team got great honors for thinking outside the box. Over 3 decades ago, preons were proposed as quark constituents, but that changed in 2005. The concept of preon stars, or nuggets in space, was developed by Fredrik Sandin and Johan Hansen of the Lund University of Technology in Sweden. Swarms of preon stars may have formed in the early universe and may still exist now. If that's the case, they'd be solid competitors for the strangest stuff in the universe. These objects would be between the size of a pea and a football, with a mass comparable to the moon, and made entirely of preons but not in the form of quarks. Their density would fall somewhere between that of a neutron star, which is the densest conventional form of matter, and that of a black hole. According to the researchers, preon stars could have formed in the early moments of the universe and lingered as a type of dark matter that interacts with ordinary matter largely through gravity. Sandin and Hansen have now computed how observers might detect preon stars using 2 distinct methods. According to Hansen, too many theorists who attempt to delve beyond convectional particle physics do not propose experiments. There are countless untestable theories, yet preon theories, on the other hand, are currently testable. The team's work is based on the assumption that a preon star should have far less mass than a neutron star or black hole, while still having a density greater than the densest ordinary stuff. The first detection method they discussed is the gravitational femtolensing, which involves a nearby preon star distorting the spectrum of gamma rays from a distant source. The effect is caused by the preon star's light-bending gravity interfering with 2 somewhat offset images of the source. The team calculated the wiggles expected in the gamma ray spectrum. They assume a preon star mass of between 1,015 and 1,023 kilograms, a range that past dark matter searches haven't ruled out. In actual gamma ray burst data, they discovered probable preon star signatures and some unexplained wiggles. Sandin and Hansen then turned their attention to gravitational waves, the as yet undiscovered vibrations in space-time assumed to be constantly blasting Earth from cosmic events. If some pairs of preon stars are near binary orbits, at least some of them should fuse and release high-frequency gravity waves. The researchers calculated the frequency and amplitude of such waves for various preon star masses and concluded that the European Gravitational Observatory, which is still in the development stages, would be able to detect merging preon stars. They also pointed out that a higher frequency detector improves the odds, such as the 100 MHz tabletop model being tested at the University of Birmingham in England. Because preon stars might slam into the Earth or Moon and go unnoticed, the researchers consider studying terrestrial and lunar seismic records as a third option. It is impressive to see that scientists are thinking outside the conventional box of particle physics. If you like this video, please consider subscribing and click the notification bell so you do not miss any upcoming videos.